Okay, so let's continue. So we have a talk about data visualization. The next, we're going to talk about data pre-processing. So this is an extremely important concept. So we have mentioned this pre-processing, and actually takes a lot of time in job of data science. So the first thing is, so this has a two part. The first part is concept, and the second part is actually the programming. So first thing is we're going to talk about is data cleaning. So so a lot of time the data has and the errors. That means it's actually has a mix match of the ground truth, and sometimes has missing values, sometimes has extreme values, and you have seen similar and situation before. So the idea is a good model should be very robust to those errors. So that means and if the data is missing, data has extreme values, those models should handle these kind of situation very well. So you can think about two different ways. The first way is this deep neural network actually trained with the stochastic and gradient descent. So this is actually very good because it's very robust to error. So if you have a missing data, if you have extremely values, this stochastic gradient descent is very much can tolerate these kind of situation. On the other hand, if you are working with a decision tree, if you have a tiny bit error, then this model will be could be dramatically different. So that means if you have extreme value, you have missing data, you have an error data. If you apply decision trees, you will have a problem. So this is something that is being studied or discussed in the theory of machine learning. Like such kind of decision trees is not very robust. Sometimes and we call it overfittings. And we're going to talk about this like overfitting issues later of the courses. So the consequences is the training data, with the error and that we have, the training data may still converge, but in a much, much slower rate. And also the accuracy will degrade because we have some error data and we have a lower accuracy. But the issue is it's very hard to detect such kind of situation with accuracy degradations. And also, if we deploy these kind of models, it will also impact the quality of new collected data. Like think about those kind of examples generated by pull recommendation of search results. You build a model based on that, then your model won't be very good. If you have a new data that comes in, and then you're trying to fine tuning and further tuning your models, it will also have that an effect since we already trained those models on like poor result or and the result has errors. So there are a bunch of errors or different types of errors that we have. This is like commonly used and commonly seen errors in this the data. The first thing is it has outliers, right? So what is outliers is the data actually significantly deviate from other observations, right? So and this is we're talking about outlier versus undersampled rare event. So this is quite different because sometimes we are interested in those rare event. That means we need to consider those outliers. But sometimes we are not interested in those outliers. We are interested in those main bodies. For example, the house pricing predictions. We are not interested in predict the house pricing that is like outside of like normal range. We are interested to predict the housing within these ranges. So basically, this is something that we already talked about in our EDAs. You can see this is data type of the value counter for the first 20 different types of house. It has all of that. You can see like most of them are concentrated in the top maybe 10 of that. But the rest of things, they only have like less than 100 counts for those types. And we consider they are outliers of the types. If we have plot this kind of box plot, and we have mentioned those dots right here is actually beyond 1.5 of box length, that means everything right here, right here, right here, they are outliers. So a very good things to think about is we might need to detect those outliers and possibly just to get rid of these outliers. I mean, this is very important because and those outliers may severely and reduce our and accuracy of the models. So this is something that we need to consider this as well. And also we're going to talk about this outlier detections, like various different packages later in the courses. So this is also very commonly asked questions. You need to consider those outliers. You need to remove those like entries actually have as being identified as outliers. The second thing is rule violations. So that means some like and data values actually violate integrity constraints, such as like not now, it cannot be now and now value, or has to be unique, has to be non-negative, these kind of things. For example, if the price is negative, it doesn't make any sense, so it must have some error here. The third one is pattern violations. Like for example, the value violated like syntactic and the semantic constraints such as formatting or misspelling. Like for example, right here, you can see we have a single family and a single family here. These two should like merge together, obviously, because they are talking about the same thing, but it was treated as a different because single family here, we have a space here, but this one that we use a lot doesn't have space. So this actually, I mean, implies it's pattern violations. Hypothetically, this is should be merged into single family without and a space right here, then emerge into the first categories, right? So, I mean, this is the one way that we can think about, or we can think about everything like single family lot could also be like rule violations or pattern violations. It can also be merged into single family as well. Okay, so so what you can do is for those kind of rule-based detection, you can design the rules to identify these. For example, you can like think about as like functional dependence. That means x, I mean, is a function and the map from x to y. That means the value of x actually uniquely determines a y. For example, if you have a zip code, it actually unique define the state. If you have an EIN, which is the like unique code to actually identify the company name, so you can have this kind of functional dependencies to ensure this kind of rule is like enforced. And you can also do like denial constraints as well. So for example, this is more flexible first order like logic. For example, if the vendor has an EIN, which is the number identify the company numbers, then the phone number cannot be empty because this is like by rule of the rules of the companies. And also if two captures of the same animal indicated by the same tag numbers, you can just say the first one must be marked as original. So like basically two things has the and mark and indicated by the same tag, and one is original, one is the copy. So just mark as the first one is the original, then the second one is a copy. Like pattern-based like detection. So basically, and you have a typos, you have a different things is like doesn't make any sense. You can have a syntactic pattern. For example, all the ENG, EN, English. You can also all map into English. So because they are talking about the same thing. And also you can map a column to the most prominent data type and identify the value doesn't fit. So basically, like, and for example, this pattern right here, you can see them, and a lot of other things right here, as you can see, right? This like single family, it should be mapped into the single family here. Here, the other ones you can think about maybe this like and a condominium right here, it should be mapped into condo here. So these two things just give you some idea. If you see something that doesn't fall into this patterns, you can map this things into the things that you think it is reasonable. And also for the semantic patterns, you can use rules through the knowledge graph. For example, we know if it has a country, it must have the capital. So if you have a Stanford as a capital, so that will be invalid because we know Stanford is not a capital of any other countries, right? So this is something that is you can have some like simple rules that to see whether it makes sense. Nowadays we have a large language models, and a lot of times we can using those kind of large language models to check whether this pattern makes sense or whether this like in the semantic patterns is a valid or not. I mean, if it is Stanford being a capital, it doesn't make any sense. So the large language model will tells you, okay, this is not working, this is wrong, and this is and they would detect that patterns and wrong data entries. So this is data cleaning. In practice, particularly for this courses, we will mostly focus on this outlier like detection. So this is something that is usually happen a lot. You will see these kind of things. But like you will also like see some like rule violation and pattern violation a little bit. But for the most of the time, we will focus on the first like outlier situations. All right, so second, other than the data cleaning, we are going to work on those like data transformations. Data transformation is very important because, and you will see that in the later of homework, if we don't transform the data, actually it will severely damage the performances of the models because almost all machine learning algorithms prefer those well-defined, fixed length, well-conditioned, nicely distributed input. It's like you can think about it as a Gaussians, and they like Gaussians a lot, and the Gaussians features. So we need to transform and apply different type of data transformation method for different data type. And we have a numerical type, we have a categorical type, we have various different types. And also we need to balance the storage quality and the loading speed. For example, I mean, for the categorical and data, we'll talk about this a little bit later, and we can do like one-hot encodings. But say we have like 200 or 300 different categories to do this one-hot encoding. It could be like, and you need a lot of storage, and it will be and you are going to increase this like features by 200 just to accommodate this one-hot encoding for that specific categorical data set. So then it might be you need to worry about this, how to balance the storage. Maybe we can using and sparsities to store those kind of and encodings and the so on. All right. So the first things, if we are working with the numerical data set, one thing that we can do is we can apply this normalization for real valued columns, because this normalization will usually make the training more stable, and a lot of cases will make things much, much better. So there are a bunch of different ways of doing this transformation. The most popular one, it's the first one and second one. We're going to talk about the third and fourth and a little bit later. So the first one is mini-max normalization. So that means I'm going to map this data like linear map to the minimum of A and maximum of B. there are two possible choices of A and B. You can do -1 to 1, so A is -1, B is 1, or A is 0, or B is 1. So if you want to work with the like neural network, a popular choice is A equal to -1, B equal to 1. But I mean, if you want to work other like traditional machine learning algorithms, you can work with A equal to 0 and B equal to 1. So, I mean, this is pretty much very simple, just a linear map from and to the minimum of A and B. So basically, the minimum value of the data set will be mapped into A, and the maximum and the value of the data will be mapped into B. And the second thing that we so we can do is the standardization. So this is also very important. Basically, we can transform this data into the distribution with a zero mean and the standard deviation being 1. So this is very common. And you can think about it, we just and reshape everything into like one single Gaussian distributions. If I mean and the Gaussian has a different mean and a different standard deviation. So basically, it's subtract the mean and divided by the standard deviations. Decimal scaling is not very popular. I'm not going to talk about this. Log scaling turns out to be quite useful. It's particularly useful when this distribution has a long tail. For example, usually people work with like age or like wealth or the price. These kind of values is actually strictly positive. Usually this I mean distribution of those features or target features and target values, they usually have a long tail, like what we talk about for the housing problems. If you actually plot the histogram of this housing price, you will see this housing price actually demonstrate the behavior of long tail. So that's why and usually what we do is we take the logarithm. Once we take the logarithm of the and housing price, this is usually behave like and behave much better here. Okay, so image. Okay, right here. So image transformations. So this is also very important. If your data is images, as I think one of the homework and you're going to work with like and so image data. So and usually, so images usually has a has a lot of like pixels. One of the issues if like nowadays if you take pictures with your phones, it actually will give you like millions of pixels of images. So you need to do some downsampling. So this is very important to save the storage because you don't want to work with like 10 terabytes like data. This is way too expensive to process, and also you have to load those image very fast. So and what we usually do is we like downsample those images into 320 by 20 and 220 and 224, and the resolution is rather low resolutions, but machine learning algorithms turns out to be very good at those kind of like low resolution images like CIFAR10, like packet like data set is like and relatively low and resolutions, but turns out many machine learning algorithms are doing a very good job on these kind of low resolutions. And also sometimes you have to be careful if you want to do some compressions or not. Sometimes if you actually to do some like JPEG and transform with a different version for high, medium, low JPEG compressions actually may lead to some percentage drops. Because if you compress the image, although like two images may look exactly the same by human eye, it has some information being lost. That kind of information lost actually may lead to the accuracy drop. Also, another things for image, and also the other one as well, it's it's called like image widening. So like, I mean, it's like generalized version of like normalization here. And you can think about, it's right here, for example, I mean, this is your original data in 2D, right? So it looked like an like ellipse. So what you do is, and you can see right here, so like in this direction right here, and the covariance is, and the variance is larger, and in this like, and like domain and the directions, and the variance is shorter. So this is something that, some information we can take advantage of this. And also, in a lot of cases, if we want to apply the machine learning algorithm, these kind of thing is not really something that, the machine learning, algorithm will be like, because these indicate, like these and these directions, and this direction are actually independent. But if we think about think about X and Y, it could be highly correlated as well, because and obviously, I mean, this is the direction has the largest and the correlations. So what we do is we can widen those. What happened here? Okay, so what happened? Okay. So this is your original data right here. So what you can do is you can, find out such kind of like and a decorrelation right here, and rotate by the angle of E, and you can like scale by D square root and square root of D. So this whole process is very much like doing the PCA, principal component analysis, such that it's basically we are trying to find a way to widen the data to make sure this data has the, I mean, in all direction has like, zero means and a standard deviation being one. It's like normalization of the data. So what we can do is we can using PCAs and to widen the data. So if we do that, it's like the model usually converge faster, with a wider and image input. So this is very commonly and the things you and we should be, consider. So that means if we are like input some like highly correlated, and highly correlated data such that the images, the first things and we should and applies the principal component to reduce the dimension from very high dimensions into relatively manageable dimensions, by doing this process, then we can apply the models. And with that, and usually the model converge faster and has a better performances. And also there will be some like video transformation. We are not going to talk about videos, but you can look at this into. But this is much and the more difficult problems to work with on videos. Text is not something we're going to talk about this in this course a lot. But one thing that we can think about is if you have seen a text, for example, descriptions of the houses, and you can see that, and you can do some like tokenizations. So that means it's you get the text strings to a list of tokens, for example, by word, by characters, by subword. For example, and this sentence says easy to load to model, increase storage space. So what you can do is you can by word, and this is the token 1, token 2, there will be token 3, and get back to token 2, and this is token 4, and so on. So like each word can be treated as individual tokens. This is actually how ChatGPT is working. Is they treat different word as a token. They try to predict what is the most likely word, and for given the sentences. So this is commonly being used in like language models. So that's like data transformation. We have talked about data transformations. We're going to talk about that in detail if we have more concrete examples. All right, feature engineering. Third part is feature engineering. Feature engineering is very, very crucial. One of the things is feature engineering is, in a lot of cases, you will see a lot of features like tens and tens of thousands of features. In fact, one of the, I mean, the house sale problems, we have almost like 2,000 features, right? And other than we do this kind of transformation, we might need to pick the most relevant features, or even transform the features into some features that we might be interested. So so feature engineering is very crucial and to using these kind of machine learning models. For example, if we think about how you're going to handle to predict the like digits with the traditional computer vision problems, and what you're thinking about is maybe you can detect the corners of those like and the like numbers, or maybe some interesting point that we can count, or these kind of things. So these are something that we should be thinking about, like if some features could be very useful, some features may not be useful. For example, the four corners of this images of the MNIST data set may not be useful because they are all like black. However, like nowadays, the deep neural network can automatically extract features. For example, like using the convolutional neural network to extract features like automatically. So like those like local informations about like these images, you don't actually need to artificially create this and these features. And the point of this convolutional neural network can actually help you to create these features for you. And since this is automatically created, so these features will be the most like relevant to the final task, and it depends what kind of task and you want to do, whether you want to do the numbers, or you want to do the objects, or you want to do some classifications of behaviors, for examples. But of course, this has some limitations if we want to using deep neural networks, because and usually that requires a lot of data. It's like very data hungry, and it's very computational heavy. The training process is lengthy, and the training process could be very expensive. And also, this is like the whole idea of the feature engineering and the feature learning. Sometimes we don't know how to create the right features, and you need to actually learn the features automatically. So think about this way. So if we actually manually engineering the feature, for example, the edge of this object, it looks like a cat. So the things you can see is, and you want to check whether they have ear or not. If they has an ear, this is more likely to be a cat. If it has no ear, this is more likely to be a dog. These kind of problems. Then this can be naturally being applied into SVM problems. However, you can also learn the features by like neural network. For example, convolutional neural networks can automatically learn the features from it, and this is what we're going to talk about in the later of the courses. Then all you need to do is you can just apply a softmax and regressions that can and that will be your last layer of neurons, and actually can make and this prediction very well. But if you like manually engineering and these features may not, and that may not be like linearly separable. So that's why you actually need to using SVM to create like a bunch of nonlinear features. And using SVM to find out like nonlinear boundaries to separate these two classes, for example, cats and dogs. But this might be the benefit for the convolutional and the networks is they created, I mean, these features, they are more likely to be separate by like linear hyperplanes, and the softmax regressions will be enough. But there will be like a trade-off for both approaches. And also these things actually, sometimes we'll cover that with a transfer learning. That means actually you don't actually need to do that and train these features. You have some like neural networks already pre-trained. For example, the AlexNet is already pre-trained. It's very large network. You don't actually need to train this network. You can just take this network and using the features they output as some like feature we learned. That means we don't actually need to tune these kind of like networks. There are a bunch of other things. For example, the tabular data. For example, this like pandas data frame, and it's very common. And it usually has a numerical features, has categorical feature, has a string features. If it is integer, you can directly use that, or you actually bind to n different like unique integer values. It depends what you need. If you have a lot of like integers, you might need to consider to bind them into like integer values. Categorical data, you can do one-hot encoding. So, and I hope you remember and what is one-hot encoding, and it has been used a lot in the past. And we're going to talk, a little bit. But one-hot encoding, you think about, first we have a cats and dogs. So that means cat is going to map into 1, 0, and dogs is going to map into 0, 1, right? So this is one-hot encoding. If you have a very rare categories, and this is like something that happens a lot, if you have the features is like it's like has vast like and a lot of other features. And for example, the one that we have talked about, the type of houses you can see right here, they have a lot of rare features, right? And we consider outliers, right? So, and what we can do is we can group all these features into one gigantic things as say unknown. And that means I don't want to further classify these like features that and only has a 10 or 20s numbers right here. It's very few of that. So we can just group them as unknowns, which turns out may have a better and may have a better way of doing so. And a lot of time we have a date and a time features. For example, the year, the month, the day of year, week of year, day of week, because there are a lot of patterns actually is periodic and it has a like season and a seasonal, monthly, and also weekly, and there's a lot of patterns, for example, and a lot of information, and a lot of things behave completely differently during the weekend and versus weekdays. And it could be like, and the behaviors and the patterns is dramatically different in different seasons. For example, those flights, and it could be dramatically different and with the different seasons. So that's why those date informations, you have to maybe further separate down into different months, different days to consider these patterns along the date. So this is very, very important. If you have that kind of date, time informations, you have to be careful and how you are going to extract these features and what kind of feature it will and make sense or not. And you can like do these kind of like feature combinations. For example, you can do Cartesian product with these two feature group. You can have a cats and dogs. You have male and a female. Then you can like Cartesian product of these two features. That becomes like 4 features, right? Text feature. In fact, this one we are going to talk a little bit. I think we are going to talk a little bit here. So, for example, things that we and talk about a lot is represent this X text as a token feature. We have talked about this. The simplest one that we use, for example, is backwards models. It has like a lot of, but that's very simple. but has a lot of like limitations. For example, dog and cat and dinosaurs. So right. So and I mean if this is my dictionary, so that means I only count how many words actually shows up. For example, cat shows up once, that will be one. And shows up twice, that will be two. Dog shows up once, that will be one. The other dinosaur is not commonly used. That will be categorized as unknown. That will be one right here. So this is the simplest possible, that we only count how many and then the frequency of the words. But of course, this is very, very crude. We are basically losing the context for this individual words, and we don't care about the orders of these words. So this is very crude. It's just backward words. And then later on, we can think and using like BERT and GPT-3 actually to output the features for those kind of the sequence of the word to get you some good idea what is going on here. And also you can do like word embedding. So, and here this is just, we are trying to like embed sentences into the backward words and basically a vector, and we're using this vector to represent this like piece of sentences here. But in fact, you can also like embed this one word into a vectors. So basically, you can vectorizing the word that is similar to words are like placing like close together. So, and for example, two words are like close to each other, then they might have similar meanings and so on. And this is very, very and useful and powerful ways. And basically, we can do a lot of and basically transfer the word into vectors, because with the vectors, we can do a lot of stuff. We can do additions, we can do subtractions, we can do inner product and so on. And that would be a very good and the representations of those and a word. Being very popular, in fact. All right, so and of course we can do like these kind of pre-trained universal language models. For example, we can do transformers. We can do like train a large amount of like data, and we can do like text embeddings, fine tunings, all these kind of stuff, right? So this is transformers. So we are not going to talk about transformers, but something that and keep in mind is being very popular in the past couple of years. At last, that will be image and video features. And traditionally, and those image will be, and we extract those image features by like handcrafted feature. We talk about this, right? So we just like see whether this cat has an ear or not, and these kind of things. But nowadays, it's all pre-trained like neural networks are very common as a feature extractors. For example, like ResNet is very popular. It's trained from ImageNet to do this kind of image classification. i3D is trained on kinetics. It's like and very suitable for action classifications. There are many off-the-shelf models available nowadays. You can just Google that and what kind of like and pre-trained and those deep like neural network, you can just directly borrow that, and you can do this transfer learning immediately if you want it. Okay, so this is something that you can like have something in your mind. Okay, so this is the concepts. In the next video, we're going to talk about how actually being implemented with the codings. All right, so this can help you some idea, and with the concepts and with also the coding part. All right.